All right, so I'm going to talk about the inductance equation and what impacts the inductance of a certain inductor. So, real quick, you could watch my last video. That's me going over like the introduction to an inductor, what it does in a circuit, what it's aimed to do, how it works. I'm going to talk about the equation here. So in the last video I made, I basically said that the amount of magnetic flux going through a certain solenoid, or yeah, we'll deal with solenoid right now. The amount of magnetic flux going through a coil will be proportional to the amount of current you get, right? So if you have more current, you get more magnetic field, right? Because magnetic field depends on current. That's Biot-Savart law, Ampere's law, whatever. Current creates magnetic field. So if I have more magnetic field, I get more flux. So this is just a proportionality statement. This is just saying, this equation literally just says that my total flux is proportional to I. That's all what this equation is saying. So I can rewrite this equation and say, well, hey, L is equal to N times the flux. And remember, this is the flux through one loop over I. I could say that, sure, but this is not saying the inductance depends on these two things. In other words, if I increase the amount of current, you might think, wow, it looks like L is proportional to 1 over I. So if I increase the current, I decrease the inductance. That's not true, because what really happens is when you increase the current, you get an increase in the amount of flux, right? Because remember, flux is proportional to your current. So L is just a proportionality constant. It is just the ratio to the total flux you would get for the amount of current you have, right? So something with an inductor with a high inductance, that just means you can get more flux for the same amount of current. It's a proportionality constant, just like capacitance, right? C equals Q over V. That is just a proportionality between the potential difference across a capacitor and the charge on that capacitor. So, therefore, what really affects the inductance of an inductor? That depends on what your inductor is. It depends on the physical properties of that inductor. So let's take the case of a solenoid. So we'll do case 1, solenoid. If I have a solenoid, which is just a fancy word for coil, I think maybe it's just the math word for what this shape is. If I have a solenoid, and let's say it has N turns and for a length L. Why not? Sure. So we can use Ampere's law to show that the magnetic field, so if there's a certain amount of current going through this thing, I can show that the magnetic field is equal to mu naught N times I, where N equals N over L, the turns per unit length. So that's pretty cool. What I can do now is I can just plug that back into the L equation. So L is equal to number of turns times flux through one turn over I. So L is going to equal N times B cross A, or B dot A, whatever, but magnetic field is going to be parallel anyways. So L is equal to, and that's the equation for flux. So N times B. I just showed, or you can show using Ampere's law, it's equal to this. So N times mu naught, little n, don't mix those up, times I over I. Hey, look, I crosses out. That's what I was talking about. Flux is proportional to I because the equation for the magnetic field in this case is proportional to I. So the I's will drop. So boom. I's drop. I get L is equal to mu naught, times area. Sorry about that. Mu naught times area times little n times big N. And mu naught area, little n is just N over L times N. So I really get the inductance of a solenoid is equal to mu naught times area n squared over L. These are all physical properties of the solid, I guess, except for the the permeability, the magnetic permeability constant of free space. But yeah, these are all physical quantities. So the way my solenoid is made impacts the inductance, not the current or the flux going through it. Let's try out for another shape. So let's try a toroid. So a toroid, or what is it called? Toroid? Toroid, sorry. I'm so sorry about that. This is my little note sheet. Thanks to Harsh. Shout out Harsh, greatest person ever. So I guess it looks kind of like, it's like the donut looking thingies. And you would have like a magnetic core or something, I don't know. You have like a little core, and then you would get some coil wrapped around it. So you can, once again, you can use Ampere's law to find and I should write toroid. You can use Ampere's law to figure out what the magnetic field is through this, like through the middle here, because you can use your right hand rule to be like, oh, it creates a magnetic field this way. So when you have current flowing through it, obviously, that is going to equal B equals mu naught N Ni over 2 pi R. I think, yeah. It's on. I think it's honestly just this equation where L is like the circumference. I think, yeah, that seems right. Let me know if I'm wrong. That's the magnetic field. Oh wait, no, yeah, no. If you use Ampere's law, this should check out. So this should be good. Now you could just do the same process. L equals, so the L due to a toroid is going to equal N times BA over I. So that's going to equal N times, so the magnetic flux is equal to mu naught Ni over 2 pi R times the current. Oh, I already said that, sorry. I meant area for BA over I. Hey, the I's dropped out again because magnetic field and flux is proportional to I. Makes sense. So really I get mu naught times N squared times the area over 2 pi R. Once again, these are all physical properties. The number of turns, the area, the cross-sectional area, the radius, all physical properties. So this should hopefully show that the inductance does not depend on the current or the flux. That's just a proportionality statement. What it really depends on is this stuff. Hopefully that makes sense. Thank you for watching this very fun educational little physics film.